that right away are not homogeneous, but they can be rewritten so that they are homogeneous or in a form that we can easily solve them. So these are differential equations that are reducible. Homogeneous form. And these will have linear coefficients. Okay, so what will happen is you will have a first order differential equation of this form. So you have a1x plus b1y plus c1 dy is plus a2x plus b2y plus c2 times dx. This is equal to 0. Okay, now there are two ways that we will solve that or solve this, and that depends on these linear expressions over here. So what we do is we let a1x plus b1y plus c1 equal to 0, and also a2x plus b2y plus c2, this is equal to 0. So you can see here I have the equations of straight lines. And with the equations of straight lines, there are two possibilities. The first is that the lines are parallel. The second is that the lines are not parallel. Okay, so if the lines are not parallel, so these represent straight lines. Okay, so we say the first case is when lines are not parallel. And we know that lines are parallel if they have the same gradient. So if these two lines have a different gradient, that means the coefficient of x, when you rewrite this in the form y is equal to mx plus c, if the coefficients of x are different, the two lines are not parallel. Then what do we do when the two lines are not parallel? What we do is we work out the intersecting point or the point of intersection. So we find the point of intersection. We call this x naught, y naught. So that is the point of intersection. We solve these two simultaneously. Then we make a substitution. So substitute as follows. So we say x is equal to this big X plus x naught. So the x that we have over here, we are going to replace it with this capital X plus x naught, and this is the x coordinate of the point of intersection. And then the same thing with y. Y is going to be this capital Y plus y naught. So everywhere we have y, we are going to put a capital Y plus y naught, and the y naught is the y coordinate of the point of intersection. Then what you will notice is after you make this substitution, the differential equation will then be reduced to a homogeneous equation, and we know how to solve the homogeneous equation. So when we have the homogeneous equation, that is when we have to make the substitution v is equal to y over x. So in this case, we'll have v is equal to capital Y over capital X instead of small y over small x. So that is the first case. So what we do is we look at these two terms and then we equate them to 0. We have straight lines. The first case is the straight lines are not parallel, so there is a point of intersection. We make this substitution, then we will get a homogeneous equation which we know how to solve. And then the second case is when the lines are parallel. So if the lines are parallel, it means they do not have a point of intersection, or they have infinitely many points of intersection. So what this means is that the two lines have the same gradient. And that is this line here and that line there. So if you were to write this in standard form, y is equal to mx plus c, you would see that your gradient is minus a1 over b1. So over here, our m is minus a1 over b1. And for the second one, our gradient is minus a2 over b2. So that is the gradient of the first line and the gradient of the second one. And since we are saying that the two lines are parallel, this means that minus a1 over b1 is equal to our gradient, which is the same as the gradient of the other line, like that. Okay, now in this case, we are also going to make a substitution like with the first case, except that the substitution we are going to make is this. So we say let y equals, y minus mx, y minus mx is equal to z. And here z is some function of x as well. Okay, so this m, it's that one and it's that one because they are the same. So you just need the gradient of one of them because they have the same gradient. Then what we do from here is we will differentiate. We have dy dx minus m. This is equal to dz dx. So is equal to dz dx. So remember, z here is not a constant, it is a function of x. So that is why its derivative is dz dx. Then what we want to do is make dz dy dx the subject, so we can add m on both sides. So we will have dy dx, this is dz dx plus m, and then this we will substitute back to our original equation, and then what we get from there will be a differential equation that is separable. Okay. Then replacing dy dx will lead to a differential equation that is separable, and we know how to solve differential equations that are separable. So let's look at some examples of how we actually do this. Number one, we have to solve dy dx, which is equal to y minus 2x minus 4 divided by x plus 2y plus 7. Okay, so here you can check right away, this is definitely not homogeneous, because if I were to divide everything by x here, I would have y over x. This would be 2, and then here I'll have over x, 1, y over x, and then this is over x. So this would not be a function of y over x, so I cannot make the substitution right away. So what I need to do instead is equate the numerator to 0, denominator to 0, and then check, do they have the same gradient? That means, are they parallel or not? Okay, so we have y minus 2x minus 4 is equal to 0. So this would mean y is equal to 2x plus 4, and then x plus 2y plus 7 is equal to 0. This would mean that y is equal to minus a half x minus 7. So the gradients are obviously not the same. So these two lines are not parallel. They are not parallel. So what we need to do is find the point of intersection. So we solve two simultaneously. So how you choose to solve it is really up to you. You can use Gauss elimination if you want to. Not Gauss elimination. You can use the ordinary elimination that we do, the substitution method, graphing if you want to, Kramer's rule even. It's really up to you. So okay, I will rewrite this. We have, okay, so I'll just use substitution since I have y is equal to 2x plus 4 and y is equal to minus half x minus 7. So I have 2x plus 4 is equal to minus half x minus 7 over 2. Okay, then all the terms with x on one side, everything else on the other side. So I'll have 5 over 2x. This is 7 over 2. That's 3.5 minus 4. That is minus 15 over 4. Over 2 rather. Okay, and then this means that x is equal to x is equal to minus 3. So this is actually our x naught, which is our point of intersection. Okay, and then now that we have x, we can work out y. We said y is equal to 2 times x plus 4, and this is minus 2. So we have our y naught, which is minus 2. So our x naught y naught, the point of intersection, is -3, -2. Okay, so now that we have that point of intersection, we make the substitution that small x is equal to capital X plus x naught, and small y is equal to capital Y plus y naught. So here I will have x is equal to big X plus -3, which is just -3. And then y is big Y plus -2, which is -2. Then this I'm going to substitute over here. So this small y, just write it. This small y is going to be replaced by big Y -2. This one is going to be replaced by big X -3, and the same thing in the denominator. So I have dy dx. So I also need to replace dy d, like this one. I mean dy dx with this one. Okay, and here, because you can see these two, they only differ by a constant, so their derivatives are the same. So we actually have that d small y d small x is equal to d of big Y d of big X. Okay, because the only difference between x and big X is a constant. So when I differentiate both sides, I'll get dx is equal to d of big X, and dy is d of big Y. So that is why these two are the same. So this will just be replaced by d with a big Y and a big X in the denominator. Okay, so I have dy dx, and now I start replacing. We had small y, so I put big Y -2, then -2 times small x, which now becomes big X -3, and then -4. Same thing in the denominator. I had small x, so I put big X -3 plus 2 times small y, which becomes big Y -2, then plus 7. Then just simplify this as far as possible. We have dy dx. This is big Y -2 minus 2x plus 6 minus 4 over x minus 3 plus 2y minus 4 plus 7. So dy dx, this is y minus 2x and then -2 and -4 make -6 plus 6, that is 0. And then in the denominator, I have 2y plus x, and then there's -3, -4, positive 7, that is 0. Okay, and now when you look at this, this is homogeneous, because if I divide the numerator by x, you'll see I have y over x. This is 2 y over x, and then this is 1, and that is by definition homogeneous. So I will say divide this numerator by big X, denominator by big X, so I have dy dx. This is big Y over X minus 2 over 2 big Y over X plus 1. Okay, and then, like we said, with homogeneous equations, we let big Y equal to V times big X, and this means that d big Y X, this is V, or we have X dV dx plus V, like we did yesterday. And now we will substitute this over there, replace this with V, replace this with V, and then we have a separable differential equation. Okay, so we say dy dx, this is x dv dx plus V. This is equal to V, is it V or 2? V minus 2. And then in the denominator, we have 2V plus 1. Okay, so this V can go to the other side. So we have x dV dx. This is equal to V minus 2 over 2V minus V, 2V plus 1. Just put it under 1 like that. So I have x dV dx. This is V minus 2 minus 2V squared minus V over 2V plus 1 x dV dx. This is V minus V, so these two will cancel. And then I can factor out the negative, 2 minus 2V squared over 2V plus 1. So we can see this plus, so we can see that this is separable because I have the x terms on one side, v terms on the other. I just need the dv with the v's and dx with the x terms. So this will be 2v plus 1 over 2v squared plus 2 dv, says minus x dx. Okay, and now we have to integrate. Okay, so we'll take the integral on both sides. So here we will definitely have to split it up. The first one, 2v over this, and then 1 over 2v squared plus 1. We can factor out the 2 there. Yeah, but we know how to integrate this anyway. Okay, so we write this as the integral of 2v over even before that, just to make the calculations easy. Since 2 is a common factor in the denominator here, I can factor it out and then multiply it on both sides. So I have the integral of 2v plus 1 over 2v squared plus 1 dv. This is minus 2 integral, this is 1 over x dx, like that. Okay, I shouldn't do too many steps at once. So I factored out the 2, multiplied it here. So that's why there's a 2 here now, and the 2's gone from there. Okay, now we integrate. We have 2v over v squared plus 1 dv, and then 1 over v squared plus 1 dv. So that is our left-hand side, and then on the other side, we have 1 over x dx. Okay, so looking at this one here, the derivative of the denominator is just 2v, so my integral will be ln of the denominator. I don't need to change anything over there. So this is ln of v squared plus 1, and here, the integral, and here the integral of this is v squared plus 1, so already in your mind you should be thinking of tan inverse, and this is tan inverse of v. And then on the other side I have minus 2 ln of x plus my constant of integration. Then we need to remember that there was no v in the question, so we write v in terms of a big Y and small x, big Y and big X rather. So this is ln of big Y squared over small x squared plus 1 plus tan inverse of big Y over small x minus 2 ln of big X plus c. And then again, we need to remember that there was no big Y and big Y and big X. Now we need to write in terms of small x and small y. So when we do that, we will have ln big Y was small y minus 2. Oh no, where was the substitution? It's here. Big X minus 3. So I make big X the subject, so it's minus 3 to the other side. So let me copy this. Okay, so this is the substitution that we made. So this means that big X is equal to small x plus 3, and big Y is small y plus 2. Okay, and then we replace everything. So this is just for us to remember. Okay, then now we substitute. We have y plus 2 squared over x plus 3 squared plus 1 plus tan inverse of y plus 2 over x plus 3, and my equal to sign is there. Let me see. Okay, and this is equal to minus 2 ln of x plus 3, and then you add your constant of integration. Okay, yeah, so you can simplify it a little bit. There isn't very much. Maybe rewrite this as a single fraction, take this to the other side and write them under a single logarithm. Yeah, again, that's just algebra. Okay, then we said the second case is when our two lines are parallel. So we should look at an example of that. So we have to solve dy dx. This is x minus y plus 1 divided by y minus x plus 1. So again, whenever you're given a differential equation, always try and classify it as the ones that we have done before you resort to reducing it. So you can check, is this homogeneous? So you divide everything by x, you see this is 1, y over x, which is what I want, but then over here I have 1 over x, so it will not qualify as homogeneous. So we must try and reduce it. And like we did with the previous one, say x minus y plus 1 is 0. This means y is equal to x plus 1. And then y minus x plus 1 is 0. This means that y is equal to x minus 1. So you can see the gradient here is 1 and the gradient over here is 1. So it means that these two lines are parallel. Then we make the substitution. So with parallel lines, the substitution we make is we let y minus mx equal to z. So remember, z here is function of x, and here our m is 1, so that means we have y minus x is equal to z. So I've replaced m with 1, which I get from here. Then just differentiate. We have dy dx minus 1 is equal to dz dx. Okay, so here this means that dy dx is equal to dz dx plus 1. Okay, and that is what we are going to substitute over here. And then we also want to replace x minus y and y minus x in terms of z. Okay, so let's do that. dy dx, this is just dz dx plus 1. So now I'm substituting. We have dz dx plus 1. And then y minus x, sorry, x minus y. Here we have y minus x. So x minus y will be negative z. So this is negative z plus 1. And then in the denominator, y minus x is equal to z. So I have z plus 1. Okay, so now I have substituted this and that into the original equation. Okay, now this, again, easy to solve. You can see that it leads to a separable differential equation. So I just subtract 1 on both sides. We have dz dx minus z plus 1, then minus 1 z plus 1. So dz dx, this is minus z plus 1 minus z minus 1 over z plus 1. So dz dx, this is minus 2z, and these two cancel over z minus 1, z plus 1. Okay, so again, like we said, this is separable. So we have z plus 1 over negative 2z. Or let me leave the negative on this side. So dz, this is negative dx. Okay, then we now just integrate. This is the integral of half or just half anyway, plus 1 over 2z dz and minus the integral of dx. So the integral of half is z over 2, and this is a half ln of z, and this is minus x plus our constant of integration. And then we replace z because there was no z in the original equation. Remember, z is just y minus x. So everywhere I have z, I am going to put y minus x, and then I am done. So I have z over 2, so that is y minus x divided by 2. Then I have plus half ln of y minus x. This is equal to minus x plus c. Okay, then again, you can always do some algebra, maybe get rid of the denominator, multiply by 2 on both sides. And remember, when you multiply this constant by 2, you just leave it as c because the answer you get is a constant. Okay, so we're not really looking at this c. I just want to see that there is a constant there. Whether the constant you get below here is one that you got by multiplying by 2 or dividing by 2, it doesn't really affect the fact that it is a constant. Or you can call it a different letter after you multiply it by 2. You can call it K or C2. It doesn't really matter. Okay, so again, like I said, you simplify. If you multiply by 2, then this negative 2x goes to the other side. You can combine it with that one. See how to work that one out. Okay, then very quickly, let's look at some of the questions from the exercise. It says 5.5. So some of these equations, they're quite long, so we won't be able to do that many. But the thing to remember is they are all done in pretty much the same way. Just remember, there's only two cases. Either the lines are parallel, that means you say y minus mx is equal to z, or they are not parallel, that means you find the point of intersection, small x is equal to big X plus the x point of intersection, big Y is equal to, small y is equal to big Y plus the y point of intersection, and then substitute. Okay, so exercise 5.1, let's look at the first one. We have dy dx. This is 2x plus y minus 2 over y minus x minus 2. So again, you can check, see that this is not homogeneous, because if I divide by x here, I'll have 2 over x instead of having all the variables written as y over x. So it's not homogeneous. What I need to do is equate each of these to 0. So I have 2x plus y minus 2 is 0. Y minus x minus 2 is 0. Then if I write this in standard form, I have y is equal to minus 2x plus 2. And here y is equal to x plus 2. Okay, so I can see my gradients are the same, are not the same rather. So there is a point of intersection that I should work out. So I solve these two simultaneously. I say minus 2x plus 2 is equal to x plus 2. This means that minus 3x is equal to 0, and therefore x is equal to 0. So if x is equal to 0, this means y is equal to 0 plus 2, y is equal to 2. So my x naught, y naught will be 0 and 2. And then here I have small x is equal to big X plus 0. So x is just equal to big X. And then small y will be equal to big Y plus 2. So that is the substitution I'm going to make. So this small x, I replace it with big X. Y replace with y plus 2, and so on. And then we need to remember that dy dx with the small letters is the same as dy dx with the big letters, because here if I work out dx is equal to dx, dy, because the only difference between them is a constant. So now just substituting, we have dy dx. This is equal to 2 times big X plus y, which is y plus 2, then minus 2. Then in the denominator, I have y plus 2 minus x minus 2. Okay, so in the numerator, those two will cancel. The denominator, those will cancel. So I have dy dx. This is 2x plus y over y minus x. And now what I have is homogeneous. So I can divide this by big X, divide by big X. So I get dy dx. This is 2 plus y over x, and then y over x minus 1. Then my usual substitution, v is equal to y over x. This means that dy dx, this is equal to v, sorry, this is, it's x dv, x dv dx plus v. Okay, so this substitute over there, and we replace this with v. So we have x dv dx plus v. This is equal to 2 plus v over v minus 1. Okay, then this v, we take it to the other side. We have x dv dx. This is 2 plus v. and then minus v times v minus 1 over v minus 1. v dx. This is 2 plus v minus v squared plus v minus 1 x dv dx. This is equal to 2 plus v, 2 plus 2v minus v squared over v minus 1. Okay, so we just need v and dv together and x and dx together. So this leaves us with v minus 1 over 2 plus 2v minus v squared dv. And this is equal to 1 over x dx. Okay, so what we need here is to make this the derivative of the denominator. So the derivative of the denominator will be 2 minus 2v. So let me just take note of that. So the numerator has to be 2 minus 2v. So first thing is I should multiply by negative 2. I just need to multiply this by negative 2. Then I will have negative 2v plus 2. Okay, so we said multiply by negative 2. Then I have v minus 1 over 2 plus 2v minus v squared. And to make sure I don't change the question, this minus 2 that I have added here, I need to remove it by multiplying by minus a half outside dv. Okay, so now you see the numerator is the derivative of the denominator, because it's minus 2v, the derivative of this one, positive 2, the derivative of that one. And then on the other side, we are just going to integrate 1 over x dx. So this is minus a half ln of 2 plus 2v minus v squared, which is equal to ln of x plus c. And again, you can always simplify this and rewrite this, multiply the negative 2 out, have your ln's on one side combine, and see where to go from there. Let's just do that. So I'm going to multiply by 2 on both sides and then take this to the other side, and then this c will go that side. So remember, if you multiply the constant by anything, you are still left with a constant. So you don't have to keep saying 4c, negative 4c, or anything like that. Just put constant. So here, say take this to the other side, multiply everything by 2. Then we have ln of x squared plus ln of, this is 2 plus 2v minus v squared. And again, I just leave it as a constant, not negative 2c. Okay, then combining these two, sorry, this is big X, but big X and small x are the same, so it doesn't really matter. Okay, so what I have here, this is ln of x squared 2 plus 2v minus v squared is equal to c. And I can rewrite this as e to the power of something. So we have x squared 2 plus 2v minus v squared. This is e to the power of c, but again, e to the power of c is a constant. So this is also equal to a constant. If it helps you, choose a different letter, let's say k, for example. And then from here, we rewrite v in terms of y and x, and here we have x squared 2 plus 2 minus y squared over x squared. This is my constant. And then now in terms of the small x and small y. So we said big X is equal to small x, so I have x squared. So remember the substitution, where was it? It's this one here. So big y, sorry, small y is big Y plus 2. So this means that big Y is small y minus 2. Okay, so I have 2 times small y minus 2 over x minus y minus 2 squared over x squared, and this is equal, just write this better. This is my constant c. Okay, and you can even multiply out the brackets. We have 2x squared plus 2xy minus 4x minus y minus 2 squared. This is equal to c. Mm, 2x squared 2xy minus 4x minus y squared plus 4y minus 4 is equal to c. And then again, this 4 is a constant. When I take it to the other side, it adds with this constant. I will still end up with a constant. So this I can also just write as this. Is equal to a constant. Okay, so remember, if I have two constants, I can combine them. My answer is still a constant. If I multiply a constant by another constant, it still leaves me with a constant. If I raise a constant to the power of a constant, I'm still left with a constant. But again, if it helps you, whenever you make an operation like here, you see the 4 went to the other side to add this one, change the letter, maybe make it K or T or something, if that helps. But I think because there's so many operations that we perform, it can get confusing. Rather stick to C is my opinion. Okay, I don't think we have time to do any more because I'm looking at these other questions. The work involved is quite long. Let me see. That's number 7. Okay, number 7 is not that long. Let's do number 7. Number 7, we have 6x plus 2y plus 3 dx. This is equal to 3x plus y minus 1 dy. Okay, so again, equate both of these to 0. Then we will have 6x plus 2y plus 3 is equal to 0. So in standard form, we have y is equal to negative 3x. So negative 3x minus 3 over 2. Okay, and then the second one, 3x plus y minus 1 is 0. This means that y is minus 3x plus 1. So again, the gradients are the same. Both of them are equal to minus 1. So we say our lines are parallel with m equal to minus 3. Okay, so now that we have our m, we know the substitution y minus mx is equal to z. So this means that y minus negative 3, so it's minus negative 3 is equal to z. And then we differentiate and then from here this means that dy dx this is equal to dz dx minus 3. Okay, so we need to rewrite this as dy dx is equal to something. So when I do that, I have dy dx. This is equal to 6x plus 2y plus 3 over 3x plus y minus 1. Okay, now I make the substitution. Dy dx is this, dz dx minus 3. This is 6x plus 2y. What I have is y plus 3x. So if I multiply this by 2, then I will have 2y plus 6x is equal to 2z. So this is equal to 2z. So I have 2z plus 3. 2z plus 3. Is that right? And then in plus, yeah, just 2z plus 3. And then here 3x plus y, that is just z. So this is over z minus 1. Okay, then this 3 should go to the other side. So I have dz dx. This is 2z plus 3 plus 3 times z minus 1 over z minus 1. So this means that dz dx is equal to 2z plus 3 plus 3z minus 3 over z minus 1. Then those two will cancel. So I have dz dx. This is 5z over z minus 1. Then separating them, I have z minus 1 over 5z. dz is just dx. Okay, then integrating, we have the integral of 1 over 5 dz minus the integral of 1 over 5z dz is equal to the integral of dx. This is just z over 5 minus 1 over 5 ln of z, which is equal to x plus my constant of integration. Okay, then again, you can multiply by 5 throughout and then rewrite z in terms of y and x. So I have z minus ln of z is equal to 5x plus c. Again, I've multiplied this c by 5, but it's still a constant, so just leave it as c. And then z, where is our substitution? So z is y plus 3x. So I have y plus 3x minus ln of y plus 3x is equal to 5x plus c, and this I can write as y minus 2x minus ln of y plus 3x is equal to a constant, or 2x minus y plus ln of y plus 3x is still equal to a constant, even though I've multiplied everything by minus 1. Okay, so again, just basic algebra to get to this. Okay, so we'll stop here, and as you can see in the exercise, there are a lot of other questions for you to try. I always say this, the most important thing